video, I'm going to teach you about resistor combinations and how to solve questions coming under these. So what is a resistor? A resistor is a passive two-terminal electrical component that implements electrical resistance as a circuit element. So I hope you all know these from all levels. Usually resistance is disadvantageous for the current flow. It is an obstruction to the current flow. But in resistors, we use this obstruction for our advantage. So in electrical circuits as well as in electronic circuits, we use resistors to control current, to divide voltage and many other purposes. So you all know the circuit symbol of a resistor is like this. You all know this circuit symbol. Of a resistor. In resistor combinations, more than one resistor is connected to a potential difference in different patterns. So in such a case, it's really important for us to find the value of a single resistor which can create the same electric effect as the resistor combination. So for that, we should find the equivalent resistance of that resistance combination. So the value of that single resistor which creates the same electrical effect as a resistor combination is called the equivalent resistance. So now let's see the types of resistor combinations. There are two types of resistor combinations. One is series combination and the other is parallel combination. Series and parallel. First, let's talk about series combination of resistors. So in a series combination, one end of a resistor is connected to the end of another resistor, like this. If I draw three resistors here, one end of a resistor is connected to the end of another resistor. So now, if you complete the circuit using wires, conducting wires and an electromotive force, you can draw it like this. We connect a battery and these will be zero resistance connecting wires. So the resistance of those conducting wires are considered zero or negligible compared to the value of the resistors. So we ignore the resistance of these conducting wires. There's actually a resistance in them. In any kind of a conductor, there is a obstruction to the current flow. But since we use thick wires and we minimize the resistance, we assume it as zero. Okay. So now if you mark the electromotive force of the battery as V and the value of the resistors as R1, R2 and R3, and we assume the current flowing in the circuit as I. In a series combination of resistors, the same current flows through each and every resistor. This I current flows through R1, R2, R3. So now if we draw a circuit equivalent to this circuit with an equivalent resistor, you can draw it like this. We use a single equivalent resistor instead of those three resistors. So if we take the equivalent resistance as R, here the same electromotive force is supplied. So the same electrical effect is created, so the same current flows through this equivalent resistor. So here also the same I current flows R1, R2, R3, and the same I current flows through this equivalent resistor R. So these two circuits are equivalent. So now let's find out the value of this equivalent resistor. So you all know the potential difference between the terminals of the equivalent resistor is equal to the addition of the potential differences between the terminals of these resistors. So you all know the potential difference between the terminals of this equivalent resistor, which is V, is equal to the sum of the potential differences between the terminals of these each and every resistor. So if we consider the potential difference across this resistor as V1, this one as V2, this one as V3, we can write a relationship as V equals V1 plus V2 plus V3 is divided among these three resistors. Okay, so you all know the same current flows through each resistor. So if we apply V equals IR for each and every resistor, V1 can be written as IR1 and V2 can be written as IR2 and V3 can be written as IR3. And for this equivalent resistor, this V is equal to IR. So now here you can see this I gets cancelled. So we can write this I gets cancelled. So we can write R equals R1 plus R2 plus R3. So now you found the relationship between the value of the equivalent resistor and the resistors which are combined in series. So in order to get the value of the equivalent resistance, all what you have to do is adding the values of the resistors which are combined in series. So this is the relationship you all should remember. And remember, a series resistor combination is considered as a potential divider circuit. Here the potential gets divided among these resistors connected in series. So that relationship can be written as, if we apply V equals IR to each and every resistor, the resistor R1, V1 equals IR1 and V2 equals IR2, V3 equals IR3. If you divide this by this, V1 over V2 equals IR1 over IR2. So this II gets cancelled. So we get V1 over V2 equals R1 over R2. So the ratio between their potential differences is equal to the ratio between their resistances. So if we divide this by this, then we get V2 over V3 equals R2 over R3. I gets cancelled. If you divide this by this, get V1 over V3 equals R1 over R3. So it is important to know this relationship because you can apply easily in questions. So finally you can write V1 is to V2 is to V3 equals to R1 is to R2 is to R3. The ratios are equal. So this is basically what you should know as the theory for series combination of resistors. Now let's talk about the parallel combination of resistors. So in a parallel combination, all resistors are parallel to each other, like this. I'll draw 3 resistors here. They are parallel to each other. So we connect them to an electromotive force or such as a battery using connecting wires. Okay, these connecting wires have zero resistance, so the potential of the battery does not drop along these connecting wires. I'll teach you about the voltage or the potential of a battery. You call it the EMF in future lessons. So for the time being, what you should know is that this potential remains the same along the zero resistance conducting wires because there is no disturbance for the flow of charges. So that potential at the negative terminal of the battery remains the same along these zero resistance conducting wires. Similarly, the potential of the positive terminal of the electromotive force remains the same along the zero resistance conducting wires. So if we consider the potential of the electromotive force as V here, and let's take the value of the resistors as R1, R2, R3. Here you can see when the resistors are connected in parallel, the potential difference acting along each and every resistor is equal to this potential of the battery. So if we consider this positive end, you can see that same, if I color it to show the same potential like this. This has the same positive potential, but along a resistor this potential drops, and here the negative potential looks like this. The potential of the battery is acting along each and every resistor. So now if you draw the equivalent resistor for these 3 resistors, you can draw a single resistor like this, and for the same electrical effect we draw the same electromotive force here. Okay, here also potential is V. Now let's take the value of this equivalent resistor as R. So now here also we use zero resistance connecting wires. So the same potential acts. It's positive potential this negative potential acts here like this. So the same potential difference exists along these three parallel resistors as well as the equivalent resistor. So this circuit is equivalent to this circuit when you use a equivalent resistor. Now let's find the value of this equivalent resistor. So what do we know here? We know that the potential difference existing across these resistors and the equivalent resistor is the same. Okay. Now what happens to the current flowing in a circuit like this? Now if the current flowing is I here, it will get divided among these three resistors. So if we take the current which flows through this resistor as I1 and this as I2 and this as I3, this same I current divides as I1, I2 and I3. So you know, according to the equation V equals IR, here V is the same for all these three resistors. Since their R vary, I should vary for each and every resistor. And here the same current I flows. So the same current I flows in this circuit. It creates the same electric effect. This resistor creates the same electric effect. Means when the same potential difference is applied, this same current flows. So as this same I current divides as I1, I2 and I3, we can write I equals I1 plus I2 plus I3 here. So if we apply V equals IR for each and every resistor, so I will be equal to V over R. So for the resistor R1, if we apply V equals IR, I1 will be equal to V over R1. If we apply V equals IR to R2 resistor, I2 will be V over R2. Similarly, I3 will be V over R3. So then for the equivalent resistor R, I will be V over R. So now you see here V gets cancelled. It's common to all. So what's the relationship you are getting here? It's 1 over R equals 1 over R1 plus 1 over R2 plus 1 over R3. So the reciprocal of the equivalent resistance is equal to the sum of the reciprocals of the resistors which are connected in parallel. So this is the relationship you should know for a parallel combination of resistors in order to find out the equivalent resistance of a parallel combination of resistors. Now you remember in series resistor combinations, I told you series resistor combinations act as potential dividers, and here parallel resistor combinations act as current dividers. What divides here is the current. That's a point you should remember. Parallel divided. Here if we apply V equals IR for each and every resistor, we can write for resistor R1 V equals I1 R1, resistor R2 V equals I2 R2, for resistor R3 V equals I3 R3. If we divide this by this, we will be getting V equals I1 R1 over I2 R2. So then you can write I1 over I2 equals R2 over R1. Similarly, if you divide this by this, you will get I2 over I3 equals R3 over R2. If you divide this by this, you will get I1 over I3 equals R3 over R1. Likewise. So So here you see the ratio between the currents flowing into resistors is equal to the inverse of the ratios of the resistors. When finding the equivalent resistance of a parallel combination of resistors, there are some important points you should know for questions. Like when you know these will be easy for your MCQs. So the first fact I'm going to teach you is when two resistors are connected parallelly, I won't draw the full circuit here. So when they have marked the two terminals like this means this resistor system is connected to a circuit, okay? So a current flows. So when two resistors are connected parallelly, let's take the resistance R1 and R2 here. The equivalent resistance of this resistor system can be written as R1 into R2 means the product of the two resistors divided by the sum of them, R1 plus R2. Okay, this you actually get this from the earlier equation we derived. From this relationship we finally get a result like this. So if I show you how it comes, from the above relationship, equivalent resistance R equals 1 over R1 plus 1 over R2. So this can be written as 2 plus R1. So then you get R equals R1 R2 over 1 plus R2. Same thing. So you derive this from that relationship. So if you remember it in this form, when two resistors are connected parallelly to each other, only two resistors, okay? The short method of finding the equivalent resistance is product of the two resistances divided by the sum of the values of those two resistors. Product divided by the sum. So this is this equation. If you remember this equation, it is really easy for MCQs. I will just show you one example. Now consider two resistors. I'll do this with values. This is 2 ohms and this is 6 ohm. If you are asked to find the equivalent resistance of this, if you take the equivalent resistance as R, You can find it straight away without doing all this using this final result. What's that? Product of these two divided by the sum of these two. So 6 times 2 over 6 plus 2, 8. So what's the answer? 3, 1, 2, 4, 3, 2, 3 over 2, 1.5 ohm. You see? You can get the answer easily. So you have to remember this short way. And another important point you should know regarding this resistors connected parallel is when the value of, here also consider 2 resistors like this. Now if the value of one resistor is very high compared to the other resistor, the equivalent resistance is equal to the value of the small resistor. Now if this is about 10,000 ohms and this is about 100 ohms, let's say, equivalent resistance here is equal to, approximately equal to 100 ohms. Why? Because actually a very small current flows through this resistor. So it's like you can basically neglect this. If you try to find the equivalent resistance in this case using this method, now let me find it for you. 10,000, R1 is 10,000, R2 is 100 by 10,100. So the answer you'll be getting is something 99.0099 ohms. See, this value is approximately equals to 100 ohms. So there's no point of doing all these calculations to find the resistance. You can take it as 100. So for like MCQs, most of the time, consider this as 100. Means when 2 resistors, one with very high resistance compared to the other, like about 100 times, is connected, the equivalent resistance is equal to the value of the smaller resistor. So that's another point you should remember. So another important point regarding the resistors connected parallel is when an infinite number of equal resistors are connected. Equal resistors, okay? Consider the value is simple R here, value of each resistor. All are equal resistors. So it extends up to infinity. To n, okay? So what you should remember is when equal resistors are connected parallelly, the equivalent resistance can be found by dividing the value of a single resistor by the number of resistors connected parallel to each other. This n is the number of resistors connected. Now if you take an example like this, here you see 4 10 ohm resistors. So equivalent resistance can be written as the value of one resistor, which is 10, divided by the number of resistors. Here the number of resistors is 4. So 10 divided by 4 equals 2.5 ohms. Also another point you should know is when resistors with very small resistance, consider a circuit like this. One resistor with 1 ohm, another with 100 ohm, another with 12,576 ohms connected parallelly. Now always in a parallel combination of resistors, the equivalent resistance is less than the smallest resistor in the resistor combination. Always it's like that. So RAB is always less than this value of the smallest resistor of the combination. So it's 1 mole. So assume if the value of the smallest resistor is 5 ohm here. So RAB is less than 5 ohm, the value of the smallest resistor. So this is an important point you should remember for questions in MCQs. You can easily select the response when you know that the equivalent resistance is less than the value of the smallest resistor. So I have taught you some 4 important points regarding resistor combinations in parallel. So I hope it will be helpful for you all for MCQs and other questions.
Thanks for watching. Hope this video was helpful. If you did, make sure to give it a thumbs up and leave a comment below. Subscribe us and click the bell icon for more videos like this.